In a remarkable astronomical breakthrough, researchers have identified 6 additional runaway stars in the Milky Way, unveiling the swiftest object of its kind observed within our galaxy. What sets this discovery apart is that 2 of these stars have shattered previous records, boasting heliocentric radial velocities that surpass any other known runaway stars. One of the stars, named J1235, reaches an astounding speed of 1,694 kilometers, 1,053 miles per second, while J0927 blazes through space at a mind-boggling velocity of 2,285 kilometers, 1,420 miles per second. Among the 6 newly detected stars, 4 belong to a category known as hypervelocity stars. These stars travel at speeds exceeding the escape velocity of the Milky Way. The team of astrophysicists, led by Karim El-Badri from the Harvard-Smithsonian Center for Astrophysics, suggests that all 4 of these hypervelocity stars are likely the outcome of spectacular type Ia supernovae. These supernovae serve as standard candles, aiding in the measurement of the universe. This groundbreaking discovery has enabled scientists to revise the rate at which these stars are born. Remarkably, the revised rate aligns with the estimated rate of type Ia supernovae. The detailed findings have been documented in a research paper submitted to the Open Journal of Astrophysics. As the researchers note, a significant population of fainter low-mass runaways may still await discovery. Whenever a star undergoes a cataclysmic explosion, the resulting force can propel the remaining matter into space at remarkable speeds. Hypervelocity stars are believed to emerge from a distinct type of supernova that imparts an even greater boost, known as the dynamically driven double degenerate double detonation (D6) supernova. To understand this phenomenon, one must consider the process of a type Ia supernova. It begins with a binary system comprising a pair of white dwarf stars. These white dwarfs are remnants of low-mass stars that have depleted their fusion material, shed most of their mass, and collapsed into a dense, luminous core. Such objects are referred to as degenerate stars. A white dwarf has a mass threshold called the Chandrasekhar limit, which is approximately 1.4 times that of the Sun. Beyond this limit, the star becomes unstable, culminating in a type Ia supernova. To reach the critical mass, a white dwarf must be part of a close binary system, where its gravitational pull enables it to accrete matter from its companion, progressively growing more massive. The subsequent events depend on the nature of the companion star. If the white dwarf extracts hydrogen from its companion, a classical nova occurs. However, if the companion star is another white dwarf with a significant surface layer of helium, the cannibalizing star siphons off the helium instead. This process leads to an augmented layer of helium on the surface of the donor star. When the helium attains sufficient pressure and heat, it undergoes rapid fusion, resulting in the production of carbon. This triggers a thermonuclear explosion akin to a classical nova but with a crucial distinction. The helium detonation generates a shock wave that triggers a secondary explosion within the white dwarf's core, creating a colossal blast. This phenomenon is referred to as the double degenerate double detonation, and it propels the donor star, the star that did not undergo 2 successive explosions, unlike its overachieving counterpart, at tremendous speeds. The velocities of these hypervelocity stars are staggering, surpassing 1,000 kilometers per second. Given that a speed of 550 kilometers per second is required to escape the gravitational pull of the Milky Way, hypervelocity stars are destined for intergalactic space. Nonetheless, the quantity of these stars and the frequency at which type Ia supernovae generate hypervelocity stars remain uncertain. Hence, El-Badri and colleagues delved into the data from the Gaia survey, an ongoing initiative to map the Milky Way with unparalleled precision, including the movements of stars as they traverse the galaxy. Their investigation unearthed 4 previously unidentified hypervelocity stars originating from a D6 event. While this may not seem like a significant number, when combined with the 10 hypervelocity stars linked to supernova events already known, it enables a more precise estimation of the actual quantity of such stars in existence. And there are likely many more to be found. In fact, our galaxy potentially hosts several speeding stars that originated in other galaxies. If a significant fraction of type Ia supernovae produce a D6 star, the galaxy has likely launched more than 10 million of them into intergalactic space, assert the researchers. An interesting corollary is that there should be large numbers of faint, nearby D6 stars launched from galaxies all throughout the local volume passing through the solar neighborhood. While faster stars exist within the Milky Way, their contexts differ somewhat. Stars orbiting the supermassive black hole at the galaxy's core can achieve extraordinary speeds, with the fastest reaching a staggering 24,000 kilometers per second as it traverses its elongated elliptical path near the black hole. However, these stars are gravitationally bound in their orbits and are unlikely to depart from the galaxy in the foreseeable future, barring an unlikely three-body interaction that propels them away. Previously, the fastest known runaway star was a binary white dwarf of D6 origin, reaching a velocity of approximately 2,200 kilometers per second, with its heliocentric radial velocity measured at 1,200 kilometers per second. By comparison, J0927 and J1235 could potentially attain total velocities of 2,753 and 2,670 kilometers per second, respectively, as calculated by the researchers. It is possible that even faster stars exist beyond our current detection capabilities, as we typically only identify the brightest ones. However, this recent discovery offers a substantial influx of data points that enhance our understanding of their locations and how to detect them. The researchers aptly state, there is now a sizable population of hypervelocity stars associated with thermonuclear supernovae. Modeling this population will ultimately make it possible to infer the formation rate of thermonuclear runaways and, ultimately, the fraction of type Ia supernovae formed through the double degenerate channel. To obtain more reliable estimates of their birth rate, we require models concerning the thermal evolution of D6 stars. Thanks for watching.